Welcome to this session. Today we deal with variables in research. A variable is a label or name that represents a concept or characteristic that varies, example, gender, weight, achievement, attitudes towards inclusion, etc. Conceptual definition uses words or concepts to define a variable. Example, achievement. What one has learned from formal instruction. Aptitude, one's capability for performing a particular task or skill. Operational definition is an indication of the meaning of a variable through the specification of the manner by which it is measured. Categorized or controlled. Types of variables. Independent and dependent variables, extraneous and confounding variables, continuous and categorical variables. Independent and dependent, that is cause and effect. Independent variables act as the cause in that they precede, influence and predict the dependent variable. That factor which is measured, manipulated or selected by the experimenter to determine its relationship to an observed phenomenon. In a research study, independent variables are antecedent conditions that are presumed to affect a dependent variable. They are either manipulated by the researcher or are observed by the researcher so that their value can be related to that of the dependent variable. For example, in a research study on the relationship between mosquitoes and mosquito bites, the number of mosquitoes per acre of ground would be an independent variable. Dependent variables act as the effect in that they change as a result of being influenced by an independent variable. That factor which is observed and measured to determine the effect of the independent variable, that is, the factor that appears, disappears or varies as the experimenter introduces, removes or varies the independent variable. In a research study, the independent variable defines a principal focus of research interest. It is the consequent variable that is presumably affected by one or more independent variables that are either manipulated by the researcher or observed by the researcher and regarded as antecedent conditions that determine the value of the dependent variable. For example, in a study of the relationship between mosquitoes and mosquito bites, the number of mosquito bites per hour would be dependent variable. Examples, the effect of two instructional approaches, independent variable on student achievement, dependent variable. The use of SAT scores, that is independent variable, to predict a freshman grade point averages, that is dependent variable. Some situations do not lend themselves to the use of the terms independent or dependent because it is difficult to discuss them in casual terms. For example, the relationship between attitude and achievement, that is, do positive attitudes cause high achievement or does high achievement cause positive attitudes? The relationship between creativity and critical thinking, that is, do high levels of creativity cause higher levels of critical thinking or do higher levels of critical thinking cause greater creativity? Extraneous and confounding variables. Extraneous variables are those factors which cannot be controlled. Extraneous variables are independent variables that have not been controlled. They may or may not influence the results. One way to control an extraneous variable which might influence the results is to make it a constant, that is, keep everyone in the study alike on the characteristic. Example, not controlling for the socio-economic status of students involved in a study of the effects of instructional technologies. Not controlling for the keyboarding skills of students in a study of computer assisted instruction. Confounding variables are those that vary systematically with the independent variable and exert influence of the dependent variable. Example, not using counselors with similar level experience in a study comparing the effectiveness of two counseling approaches. Not using the same test to measure the effectiveness of two instructional approaches. Continuous and categorical. Continuous variables are measured on a scale that theoretically can take on an infinite number of values. Example, test scores range from a low of 0 to a high of 100. Attitude scales that range from very negative at 0 to very positive at 5. Categorical variables are measured and assigned to groups on the basis of specific characteristics. Example, gender, male and female, grade level K-12, socio-economic status, low, middle and high. The term level is used to discuss the groups or categories. Gender has two levels, male and female. Socio-economic status has three levels, low, middle and high. Continuous variables can be converted to categorical variables, but categorical variables cannot be converted to continuous variables. IQ is a continuous variable, but the researcher can choose to group students into three levels based on the IQ scores. Low is below a score of 84, middle is between 85 and 115 and high is above 116. The damage caused by confounding variables. For example, a research group might design a study to determine if heavy drinkers die at a younger age. They proceed to design a study and set about gathering data. Their results and a battery of statistical tests indeed show that people who drink excessively are likely to die younger. Unfortunately, when the researchers do a cross-check with their peers, the results are ripped apart because their peers live just as long. Maybe there is another factor not measured that influences both drinking and living age. The weakness in the experimental design was that they failed to take into account the confounding variables and did not try to eliminate or control any other factors. For example, it is quite possible that the heaviest drinkers hailed from a different background or social group. Heavy drinkers may be more likely to smoke or eat junk food, all of which could be factors in reducing longevity. A third variable may have adversely influenced the results, minimizing the effects of confounding variables. In many fields of science, it is difficult to remove entirely all the variables, especially outside the controlled conditions of a lab. A well-planned experimental design and constant checks will filter out the worst confounding variables. For example, randomizing groups utilizing strict controls and sound operationalization practice all contribute to eliminating potential third variables. After a research, when the results are discussed and assessed by a group of peers, this is the area that stimulates the most heated debate. When you read stories of different foods making you die young or hear claims about the next superfood, assess these findings carefully. Many media outlets jump upon sensational results but never pay any regard to the possibility of confounding variables. In many fields of science, it is difficult to remove entirely all of the variables, especially outside the controlled conditions of a lab. The difficulty of the isolating variables. In biology, social science and geography, for example, isolating a single independent variable is more difficult and any experimental design must consider this. For example, in a social research setting, you might wish to compare the effect of different foods upon hyperactivity in children. The initial research and inductive reasoning leads you to postulate that certain foods and additives are a contributor to increased hyperactivity. You decide to create a hypothesis and design an experiment to establish if there is solid evidence behind the claim. The type of food is an independent variable, as is the amount eaten, the period of time, and the gender and the age of the child. All of these factors must be accounted for during the experimental design stage. Randomization and controls are generally used to ensure that only one independent variable is manipulated. To eradicate some of these research variables and isolate the process, it is essential to use various scientific measurements to nullify or negate them. For example, if you wanted to isolate the different types of food as the manipulated variable, you should use children of the same age and gender. The test groups should eat the same amount of the food at the same times, and the children should be randomly assigned to groups. This will minimize the physiological differences between children. A control group acting as a buffer against unknown research variables might involve some children eating a food type with no known links to hyperactivity. In this experiment, the dependent variable is the level of hyperactivity, with the resulting statistical test easily highlighting any correlation. Depending upon the results, you could try to measure a different variable such as gender in a follow-up experiment. Hypothesis. A hypothesis is a specific statement of prediction. It describes in concrete rather than theoretical terms what you expect will happen in your study. Not all studies have hypotheses. Sometimes a study is designed to be exploratory. There is no formal hypothesis, and perhaps the purpose of this study is to explore some area more thoroughly in order to develop some specific hypothesis or prediction that can be tested in future research. A single study may have one or many hypotheses. Hypotheses are tentative statements of the expected relationships between two or more variables. There is significant positive relationship between self-concept and math achievement. The class using math manipulatives will show significantly higher levels of math achievement than a class using a traditional algorithm approach. Reasons for using hypothesis: provides specific focus, provides for testing of the relationship between variables, directs the investigation, allows the investigator to confirm or not confirm relationships, provides a framework for reporting the results and explanations deriving from them. When supported, provides empirical evidence of the predictive nature of the relationships between variables, provides a useful framework for organizing and summarizing the results and conclusions. A hypothesis must be testable, taking into account current knowledge and techniques, and be realistic. If the researcher does not have a multi-million-dollar budget, then there is no point in generating complicated hypotheses. A hypothesis must be verifiable by statistical and analytical means to allow a verification or falsification. In fact, a hypothesis is never proved, and it is better practice to use the terms supported or verified. This means that the research showed that the evidence supported by the hypothesis and further research is built upon that. Types of hypothesis: inductive and deductive. Inductive hypotheses are formed through inductively reasoning from many specific observations to tentative explanations. Deductive hypotheses are formed through deductively reasoning implications of theory. Research or statistical. Research hypotheses are conjectural statements of the expected results. Directional. A specific outcome is anticipated. Example, the class using manipulatives will demonstrate higher achievement levels than the class using a traditional instructional approach. Non-directional. An outcome is anticipated but the specific nature of it is unsure. Example, there will be achievement differences between the groups of children using cooperative group strategies of individualized instruction. Statistical hypothesis. They are defined as assertion or conjecture about the parameter or parameters of a population, for example, the mean or variance of a normal population. They may also concern the type, nature or probability distribution of the population. Statistical hypotheses are based on the concept of proof by contradiction. For example, say we test the mean of a population to see if an experiment has caused an increase or decrease in mean. We do this by proof of contradiction by formulating a null hypothesis. They are statements of a relationship or difference that can be tested statistically. Null hypothesis. A statistical statement that no difference or relationship exists. It is a hypothesis which states that there is no difference between the procedures and it is denoted by H0. For the above example, the corresponding H0 would be that there has been no increase or decrease in the mean. Always the null hypothesis is tested, that is, we want to either accept or reject the null hypothesis because we have information only for the null hypothesis. This is purely statistical in nature. This does not represent the outcome anticipated by the researcher. Alternative hypothesis. It is a hypothesis which states that there is a difference between the procedures and it is denoted by HA. Criteria for evaluating research hypothesis. Stated in declarative form. Consistent with known facts, prior research or theory. Logical extension of the research problem. States an expected relationship between two or more variables. Can be tested. Is clear and concise. Type 1 and Type 2 errors. Type 1 error or error of the first kind and Type 2 error or error of the second kind are precise technical terms used in statistics to describe a particular flaws in a testing process where a true null hypothesis was incorrectly rejected. Type 1 error or where one fails to reject a false null hypothesis, that is type 2 error. Type 1 error. A type 1 error, also known as an error of the first kind, is the wrong decision that is made when a test rejects a true null hypothesis H0. A type 1 error may be compared with a so-called false positive in other test situations. The rate of the type 1 error is called the size of the test and denoted by the Greek letter alpha. It usually equals the significance levels of a test. In the case of a simple null hypothesis, alpha is the probability of a type 1 error. If the null hypothesis is composite, alpha is the maximum of the possible probabilities of a type 1 error. Type 2 error. A type 2 error, also known as an error of the second kind, is the wrong decision that is made when a test fails to reject a false null hypothesis. A type 2 error may be compared with a so-called false negative in other test situations. Type 2 error can be viewed as the error of excessive skepticism. The rate of the type 2 error is denoted by the Greek letter beta and related to the power of a test, which equals 1 minus beta. What we actually call type 1 or type 2 error depends directly on the null hypothesis. Negation of the null hypothesis causes type 1 and type 2 errors to switch roles. The goal of the test is to determine if the null hypothesis can be rejected. A statistical test can either reject, prove false, or fail to reject, that is, fail to prove false a null hypothesis but never prove it true, that is, failing to reject a null hypothesis does not prove it true. Consequences of type 1 and type 2 errors. Both types of errors are problems for individuals, corporations, and data analysis. A false positive with null hypothesis of health in medicine causes unnecessary worry or treatment, while a false negative gives the patient the dangerous illusion of good health and the patient might not get an available treatment. A false positive in manufacturing quality control with a null hypothesis of a product being well made discards a product which is actually well made, while a false negative stamps a broken product as operational. A false positive with null hypothesis of no effect in scientific research suggests an effect which is not actually there, while a false negative fails to detect an effect that is there. Based on the real life consequences of an error, one type may be more serious than the other. For example, NASA engineers would prefer to throw out an electronic circuit that is really fine, null hypothesis H0 not broken, reality not broken, action thrown out, error type 1 false positive, than to use one on spacecraft that is actually broken, null hypothesis H0 not broken, reality broken, action use it, error type 2 false negative. In that situation, a type 1 error raises the budget, but a type 2 error would risk the entire mission. Minimizing errors of decision is not a simple issue. For any given sample size, the effort to reduce one type of error generally results in increasing the other type of error. The only way to minimize both types of error without just improving the test is to increase the sample size, and this may or may not be feasible. In this module, we discussed about the variables in research. Continuous variables are measured on a scale that theoretically can take on an infinite number of values. Categorical variables are measured and assigned to groups on the basis of specific characteristics. What are the damages caused by confounding variables and how to minimize it? The weakness in the experimental design was that they failed to take into account the confounding variables and did not try to eliminate or control any other factors. Next, we discussed about what is hypothesis. A hypothesis is a specific statement of prediction. It describes in concrete terms what you expect will happen in your study. Not all studies have hypotheses. In fact, a hypothesis is never proved, and it is better practice to use the terms supported or verified. This means that the research showed that the evidence supported the hypothesis and further research is built upon that. Then we discussed about the types of hypothesis. Then we discussed about the types of errors, type 1 and type 2 errors. Minimizing errors of decision is not a simple issue. For any given sample size, the effort to reduce one type of error generally results in increasing the other type of error. The only way to minimize both types of error without just improving the test is to increase the sample size, and this may or may not be feasible. Here are some assignments you to work out. Write a note on hypothesis. What are the types of errors? Formulate a null hypothesis. Here are some books for your references. The design of experiments. Fisher R.A. Oliver and Boyd, Edinburgh, 1935. Research methodology, methods and techniques. Kothari C.R. New Delhi, Ville Eastern Limited, 1985. Research methodology, a step-by-step guide for beginners, 2nd edition. Kumar and Renjit, Singapore, Pearson Education, 2005. On the use and interpretation of certain test criteria for purposes of statistical inference. Neyman J. Pearson E.S. London, Cambridge University Press, 1967. Hope you have enjoyed this session. See you next time. Take care.